In this video, I want to take a look at LRC circuits and the notion of resonance. Remember, LRC would be L for the inductance, R for the resistance, and C for the capacitance. In this case, I want to look at forced vibrations. So there will be sorry, I don't know if you can hear the rooster crowing. There'll be a voltage source. Okay. I've had a fair amount of experience with these because we used to own a commercial lighting business, and we would do parking lot lights, among other things. And the parking lot lights have a circuit very similar to this, not exactly like this, but there's an inductor, there's a capacitor, and there's a light bulb. The difference is the voltage source here I have in series with all of them, and the driving force in the light bulb circuits is actually that the inductor is a transformer. So the power is coming into one side of the transformer, which is inducing a magnetic field, which then produces current in the other coil. There's two coils on the transformer there. And so there is a forcing function, but it's forcing it in a little bit different way than this. But the effect is still very similar, that you've got this loop with the three components, and then somehow there's a vibration forcing it. Now, what I have right here is the inductor and the capacitor I have set up so that they want to vibrate by themselves in about one cycle every 5 seconds. So about 0.2 hertz cycles per second. The voltage source here is currently doing 1.37 hertz, so it's not vibrating at the same frequency that these two want to vibrate at. And because the light bulb is there, that's a resistance, it damps out everything that the steady state, it damps out the transient solution, right? It damps out the stuff that we would get from the homogeneous equation. And you see only the steady state solution, which is very closely tied to the frequency of the voltage source here. And that's what you're looking at. I'm looking at the amps flowing through the wire there. And you can see just maybe 1 amp going back and forth. Even if I take the light bulb and say make it zero resistance, so this is now undamped, I still don't get much different than what the voltage source is. However, if I were to change the frequency closer to what they want to vibrate at anyway, actually I'm going to throw in a lot of resistance just to damp out everything that might have been there before. So you can see there just essentially now, because there's a lot of resistance taking out anything that was there, you're now seeing just the effect of the forcing function. Now take this off. This will allow the capacitor and the inductor to do their own thing in conjunction with the forcing function, and you see that we get a bit more amplitude than we had before. So we're doing, there's still a little bit of the up and down, but we're doing maybe 2 or 3 amps here. I'd say about 2. Move this a little closer to 0.2. Put it down at about 0.5. Again, I'm going to put in a lot of resistance for a moment to damp out whatever was there before. And then back to resistance 0. And we can see that this gives me even more amplitude. Actually, what this is looking like to me is starting to look like a beat, because I see a pretty big amplitude there, but then smaller amplitude for a bit, and then a big amplitude again, and a smaller amplitude. Am I starting to see beats? Well, it's undamped in this case, so yes, I think I am. Let's move this a little closer to 0.2. Let's put it at, let's say, 3. Again, just for the moment, let me take out everything that was there before by increasing, putting a lot of damping on there. Transient state fades out. You have just the steady state solution, which is essentially the same frequency as the forcing function. And then take the resistance off and let the inductor and capacitor have some influence on this. And what I see here, whoa, I see that getting so much that this is thinking that my circuit is going to burn itself up. I get really big amplitude here, undamped. But oh, look at this is coming back down again. So yes, I am seeing a beat. This is coming down to very small, and then it'll build back up again. The natural frequency of the inductor and the capacitor here is 0.2 cycles per second. I'm forcing it at 0.3 cycles per second. So they're close, but they're not quite the same, and so I get these beats. Lots of current down to no current. If I get this to be at 0.2, let me put in some resistance here again to kill off anything that was there. Alright, now let's let her rip here. And this is, again, I don't know if 0.2 is exactly right. The period is a little bit less than 5 seconds, so the frequency isn't quite 0.2, but 0.2 is really close to what it is, and we should see this build to higher and higher velocities. In fact, this is telling me that the animation speed has been reached. The simulation isn't keeping up with what it needs to be. Okay. So this is what happens with resonance. This is undamped. Okay. Now, with a light bulb in there, you have some damping happening, and it will bring this. I hope this brings this under control. Yeah. But still, what I have is, what is that? It's about 5 amps at the moment. Yeah, so this is going back and forth at about 5 amps, which is more than what we had before. I have the same resistor, whether the frequency is up here at 1.5. This is the forcing function frequency. Right? This has the light bulb barely lights. Or bring it down to 0.2, and you get much more flow through it. I'm not changing the voltage. I'm not driving this any harder. I'm just driving it at a different frequency. Now, when you're out in the field, changing a light bulb in a parking lot, and the light bulb doesn't light when you screw it in, it's because probably the capacitor, but sometimes the inductor needs to be replaced. So you got to put a new capacitor in. Well, sometimes you don't have the right capacitor with you, and you put in something a little bigger or a little smaller. And what happens is that you've changed the natural frequency of the inductor and the capacitor working together, and you're either going to be driving that light bulb a little harder than it needs to be driven, or a little less than it needs to be driven. So you're going to be getting too much light out of it, which is going to burn it out too fast, or it's just going to seem dim because it's not getting enough amperage to it. And in the case of the parking lot lights, they're an arc tube, so they need a particular amount of amplitude to send the spark through the tube, and so they might not even light at all if you're not driving it right. So there's a play. When you're up there putting in a new capacitor, you're not changing the frequency of the forcing function. You're changing the natural frequency between the inductor and the capacitor, because you put a different capacitor in than what's supposed to be there, and so it may not work right. It's interesting in that I've asked the question many times in various trainings and whatnot. Why do we use one particular capacitor with a particular inductor? It turns out that we're not maximizing the current. We're just getting enough current to drive the light bulb without blowing the light bulb out. Because as you can see, I can get a range from, well, about 1 amp to about 5 amps on this thing just by changing the relationship between the forcing frequency and the natural frequency. Okay. So when you're an electrical engineer out there, these are the kind of things you're going to have to be designing and keeping track of, and making sure that you're not overdriving stuff and burning things up too quickly because you haven't paid attention to the natural frequency versus the forcing frequency. So anyway, there's LRC circuits and how they fit in with this vibration stuff.